Hello. Last time we talked, we defined the Lebesgue measure, and we finished talking about the Lebesgue measure, and we started talking about the Lebesgue integral, and we got to the point where we were able to define the Lebesgue integral. And what I'll do today is just wrap up some things about the Lebesgue integral, and then talk about why it's a useful thing for us. Okay. So first, I had defined the Lebesgue integral last time, so I will not be reminding ourselves of that definition. But what I will do is just say a bunch of things that are true, and maybe I'll explain some of them, but I won't prove any of them. So the first thing that's interesting is none of our constructions for the Lebesgue integral are particular to Lebesgue measure. Okay, so so what we did was we took an interval I and R, and we considered certain kinds of functions, the real valued functions defined on the interval I, and we defined an integral for those. And how did we do that? Well, we started with the notion of a measurable function. Okay, and what was the definition of a measurable function? It was that the preimage of a certain interval, possibly including infinity, that the preimage of that should be measurable in the sense that it's a measurable subset of the domain, which in our case was I, the interval I, but you can certainly imagine doing exactly that construction for functions, real valued functions on an arbitrary space with a sigma algebra of measurable sets and a measure defined on that sigma algebra. Okay, because all it needed was the notion of a measurable set. Okay, then what did we do? We defined simple functions. Okay, and simple functions were finite sums of characteristic functions, so functions that were constant on some measurable set. Okay, there's nothing about simple functions that's particular to the Lebesgue measure. You can talk about a simple function, again, on an arbitrary measure space, okay? Then we had, I told you that you could approximate measurable functions with simple functions. Same thing is true on an arbitrary measure space. And then we took to integrating, okay? So we defined the integral of a simple function. The definition of the integral for a simple function on an arbitrary measure space is exactly the same as the one we gave for when we're using the Lebesgue measure. And then you define the integral for positive functions, and then you define the integral for not necessarily positive functions, okay? And so that process is exactly the same. And so the upshot of all that is that we can define an integral for an arbitrary measure space. X, A, mu, okay? And so again, the construction is exactly the same. And so as an example of this, is for the counting measure on well, maybe be as general as on a discrete time domain T. Okay, so remember that the counting measure, we talked about that as a simple example of a measure, well, an outer measure, but it's also a measure. When we first introduced those ideas, and the counting measure just takes a subset of this discrete time domain T and returns some finite number if that set is finite with that number of elements in it, and infinity otherwise. And if you go through this process of defining the integral on that measure space, just as I defined last time for the Lebesgue integral, and so in this case, the integrable functions are those satisfying that the sum where all t's and t, f of t is less than infinity. Okay, which we've seen before. We called that space little L1. Okay, and so the point is that this more flexible definition of measure, not just for the Lebesgue measure, but for an arbitrary measure, includes as a special case discrete time signals. Okay, we won't make very much use of that, but it's an interesting observation. Okay. You can integrate not just real valued functions, but complex valued functions. And in fact, you can very easily extend the integral not just to complex valued functions, but to functions which take values in an arbitrary finite dimensional vector space. And then it's interesting to think about how you extend the definition for functions which take values in an infinite dimensional vector space with some kind of structure like, say, a norm. Okay, so let me say a few words about that. Okay, so first, so let me maybe do this case by case. One can define the integral and integrability okay, and I mean the Lebesgue versions of both of those things for complex valued functions by applying the constructions in the real valued case to the real and imaginary parts of the function. Okay. Okay, so that's how you extend the discussion to complex value functions, and we're definitely going to make use of that. More generally, because C, after all, is just a two-dimensional real vector space. And so you can imagine applying the constructions to an n-dimensional real vector space. Okay. So we can consider V valued integrable functions. And their integrals. Okay, so to do this, you can just proceed, kind of brute forcey to reduce yourself to the case of real valued integrals, just like we did in the complex case, right? So we just took a complex valued function and broke it down to its real and imaginary parts and did the same thing for the real and imaginary parts. So we'll do something here that's entirely analogous by choosing a basis, which is essentially what we did in the complex value case. So in the complex value case, we chose the basis 1i. Here, we're just going to choose some basis. For V, and write F from, let's say we're talking about functions defined on an interval I. So let's look at the Lebesgue case rather than the more general case of a measure space that I talked about out there, although you can just as easily do that. Okay, so if you have a function f, you can write f like this. Okay, so you can always do that regardless of what f is, just because the e's form a basis. So then one can say f is integrable, and again, this means Lebesgue integrable, because I'm working with the Lebesgue measure on I. If f1 n. Okay, so these these now are going to be real valued functions. Okay, and if V is a complex vector space, they can be complex valued, and then we're just going to reduce yourself to the real value case by our previous construction. Okay, so F is integrable if all the components of F are integrable. And the integral is integral over I f d lambda is integral over I f 1 d lambda times E1 plus n Okay, so the obvious thing. Okay. Okay. And we will make use of this when we talk about systems, because we're going to be talking about systems in a context sufficiently general that we'll be working with finite dimensional real vector spaces. However, you can be even more general than this. So you can consider an infinite dimensional real vector space V and functions taking values in V. And again, we'll just work with the Lebesgue measurable case, although the constructions or the context can certainly be extended to the situation of an arbitrary measure space. Okay, now in this case, things aren't so straightforward about how you define the integral. Certainly you need some kind of a structure there. You know, one sort of algebraic way to do it, which as far as I'm aware is not useful, is to use the fact that every vector space has a Hamel basis, and so you could imagine repeating these constructions for Hamel basis. But that's, again, that's not a useful construction as far as I'm aware. Typically, the way you do it is you have to consider some kind of structure on V, some kind of analytical structures like a norm, and you use that to sort of mimic the general process, which is you talk about simple functions, and then you talk about the integral as being a limit of integrals of simple functions. Right? That's typically the way one does it. But there are, well, I shouldn't say that's typically the way one does it. There's many ways, actually, in the case of an infinite dimensional vector space, to think about what the integral might mean. And the way I just mentioned, approximating by simple functions, is one way. Okay, and that gives rise to what's known as the Bachner integral. Okay, so I'm not going to go into that here. So in this case, one must put some structure on V, for example, a norm. Okay. All right, but in the normal real valued case, and in the complex valued case, and in this case, okay, there's a simple characterization of integrability. You know, the integral remains the way I've characterized it. The way I've characterized it here and here, and previously for just real valued functions. But there's a simple characterization of integrability in those cases. Let me tell you what that is. So, in for functions f from I to V, where V is finite dimensional, And so, this includes as a special case, therefore, the scalar cases. It's easy to show that a measurable f is integrable if and only if if the norm is integrable. Okay, and so this is a way to check integrability. Rather, you can check. So in the complex case, the construction we give here is that you check integrability on the real and imaginary parts separately. In the finite dimensional vector valued case, you check integrability of each of the components of the function separately, and that gets you integrability. And even in the real valued case, what do? You check the positive and negative parts of the function, and both of those have to be finite valued in order for you to be integrable. And this one condition about the integrability of the norm. And so in the particular case of v equals r and v equals c, of course this amounts to just the absolute value or the complex modulus. Okay. And certainly in the case of v equals r, which is the case we covered last time, what this is saying then is that f is integrable if and only if its absolute value is integrable, and that's clear from the definition we gave of integrable, because we required both the positive and negative part of f to be integrable, and so that means that, and then we define the integral to be the difference of those things. Well, the integral of the absolute value is just going to be the sum of those things. Okay. And so this is connected absolutely, or I should say, this is connected exactly to our discussion of absolute and conditional integrability for the Riemann integral. Okay, so let me mention that. Oops. Okay, and so we are here talking about absolute integrability. Okay, so integrability of the absolute value, or in this case, more generally, the norm. Okay, and so I guess I put some norm here on the vector space, and because remember we talked about norms on finite dimensional vector spaces all being equivalent, so it doesn't matter what norm you use here. Okay, and so you can talk about conditional integrability, for functions defined on, say, all of R, right? And so if you have a measurable function defined on all of R, there's constructions that you could do for the Lebesgue integral, rather like we did for the Riemann integral, where you truncate the function at some finite capital R, and then integrate from say 0 to R and from minus R to 0, and consider then taking the limit as R goes to infinity of both of those bits. And defining a conditional integral in that way, right? And when we actually will have occasion to talk about that conditional integral when we talk about Fourier analysis. Okay. Okay, so other facts. Oops. So the Lebesgue integral is linear. Okay, so if f and g are Lebesgue integrable, and if you have a constant alpha, so let me leave it as R for the moment. It can be extended to the complex case, but I'm only talking about the real case. Then f plus g and alpha f are Lebesgue integrable. And the integral of the sum is the sum of the integrals. Okay. All right. Okay, so that's good. So let's talk about the relationship between the Lebesgue integral and the Riemann integral. Okay. So if f is Riemann integrable, then it is Lebesgue integrable. Okay, and the two integrals agree. Okay, so this was our notation for the Lebesgue integral, and this is our notation for the Riemann integral. However, because of this fact, we will often just write the Lebesgue integral like this because it's convenient to do so. But unless I say otherwise, and there's no particular instance when we would ever want to use the specific properties of the Riemann integral. So we're always going to be talking about the Lebesgue integral in this course. And so I may just use that notation. So we'll often write the Lebesgue integral in Riemann integral notation. Okay, so from now on, if I write this, I do mean the Lebesgue integral. Sometimes I'll want to be careful and write that, but sometimes I will be just as happy writing that. Okay. All right, so it's interesting then to think about what are the relationships between the Riemann integral and the Lebesgue integral. Okay. So in particular, it's interesting to know when is the function Riemann integrable. Okay, so we have a construction of the Lebesgue integral, and it starts with measurable functions. Okay, and so the characterization of when a function is Lebesgue integrable, it is just what the definition says it is, right? You have two constructions that you do using the positive and negative parts of a function f, and if both of those give you something finite, then it's Lebesgue integrable. Okay, and that's it. For the Riemann integral, we had this approximation using upper and lower step functions, and it's interesting to think about when there's a cleaner characterization of what Riemann integrability means, and there is one, and it's kind of beautiful. Okay, so if f is, and so we go back to the original setup for defining the Riemann integral, and that is a bounded function defined on a compact interval. So in that setup, that's where we originally defined our notion of Riemann integrability. So then f is Riemann integrable if and only if f is continuous almost everywhere. Okay. So this means that the set of points at which f is discontinuous has measure 0. That's our characterization of that statement, right? And so the characterization of Riemann integrable functions is done by the Lebesgue measure. Okay. All right. And so, for example, okay, this function, which was, so this was our original example of a non-Riemann integrable function. Okay, so 1 on the rationals between 0 and 1, and 0 on the irrationals between 0 and 1. Is discontinuous everywhere. Okay, and so that's certainly consistent with our observation, direct observation, that function is not Riemann integrable. Okay. All right, so since we're talking about the Riemann integral, and one of the things we observed about the Riemann integral that was distasteful is that it interacted poorly with pointwise limits. Okay, let's see how well the Lebesgue integral improves that situation. Okay, so we have convergence theorems. For the Lebesgue integral. Capitalize that. Okay, and we'll look at two of those. Okay. All right, so the first is what's called the monotone convergence theorem. Okay, and this is quite flexible as compared to the next one we're going to give. So, you know, its flexibility is best made in claimed when I contrast it to the next one. So let me just state it and then I'll compare the two of them. Okay. All right, so the theorem says we're given a sequence Fj of measurable functions satisfying. Okay, so they're monotone, and what the monotonicity here that I'm talking about is that the values of these functions increase with j. Okay, so it satisfies f j plus 1 of x is greater than or equal to fj of x for j in positive integers. And for almost every x in I. Okay, so apparently I'm talking about measurable functions defined on some interval I in R. Okay. All right, so then, okay, the limit as j goes to infinity, integral over I, f j d lambda, and I'm going to use Lebesgue integral notation here because it's important to emphasize that this is a statement about the Lebesgue integral. Okay, is equal to the integral over I of the limit. Oops. Okay, and this means pointwise limit. Okay, and also this limit could be infinity. Okay, so these are oh, and I'm very sorry. These are all positive functions. Okay. All right, but I do allow them to take the value of infinity. Okay, and so it could be the case, for example, that at a certain x, okay, if you fix an x, that this sequence fj of x diverges to infinity. That's absolutely allowable, and that could happen even in such a way that this limit, the integral of the limit, is infinity. That's no problem, right? So I don't have an issue with these integrals on either side here being infinity. Okay, so this statement holds even when there's infinities involved, is the point. Okay. All right, so that's the monotone convergence theorem. And so let me sort of give you a quick example of this. Okay, so on the on the compact interval 0, 1, I'm going to consider what we talked about this function. We talked about the Riemann integral. So it's 1 over root x. Let's say for x between 0 and 1, and I'll take it to be whatever I want. 0 at 0. Okay. Okay, so now let xj be a sequence in 0, 1 that converges monotonically okay, so meaning that xj plus 1 is less than or equal to xj, converges monotonically to 0. Okay, so for example, the sequence 1 over j, it doesn't really matter. Define fj of x. So this is going to be my original function, but now what I'm going to do is I'm going to chop this off at xj and to be 0 like so. Okay, all right, and so so the situation is like this. So 0, 1. Okay, so f diverges to infinity at 0. Okay, and so my sequence fj xj sort of looks like this. Okay, and so I oopsie. All right, and so I'm going to chop off. So f1 will be the function which is there, and then 0. f2 will be the function which is there, and then 0. x3 there, and then 0, and so on. Okay. All right. So then by the monotone convergence theorem, okay, we have, okay, so this is a, this sequence fj will have this monotonicity property of the theorem, right? That's the crucial thing. So we'll have then the integral over 0, 1 f d lambda is going to be the limit as j goes to infinity, integral 0, 1 fj d lambda. Okay, now these integrals are calculable because these functions, you know, f1 and f2 and f3 and so on are Riemann integrable. Okay, so we can calculate their integrals. You know, in any Riemann integral, its Lebesgue integral is going to agree. So the, you know, the computation of the integral is just whatever techniques you learned for doing integration in calculus. Okay. And so this, remember, we sort of looked at this before. So this is 2 root x between x, j, and 1. Okay, so that, in other words, that's 2 root x j minus 2. Okay, and then, sorry, and then we're taking the limit as j goes to infinity of that. Okay, and the limit as j goes to infinity of that is why am I getting that to be minus? Oh, sorry, I apologize because I got my limits wrong here. 1 xj. Okay, so it's the other way around. So minus plus. Okay, so that's 2 is the point. Okay, so that's a sort of use of the monotone convergence theorem to do something elementary. Okay, so that's the monotone convergence theorem. And that's only for monotonic sequences of positive functions, right? So it's very powerful because it doesn't have a lot of hypotheses, but it's very restricted because of the monotonicity requirement and the positivity requirement. And so the next convergence theorem relaxes those, but you pay a price in a different direction. Okay. Okay, so again, we start with a sequence. Be Lebesgue integrable on I, and suppose that there exists a Lebesgue integrable G, and I'm going to require here the G be non-negative, okay? And if G is not non-negative, I could take its absolute value, so G may as well be non-negative. Okay, and the requirement here is that okay, is that the FJs, okay, the crucial thing here is that this holds for every J. Okay, so for almost every X, okay, this holds for every J is how to think about that. And so the point, the crucial thing is uniformity in J, okay? So there's a single G, non-negative, that bounds these things in absolute value for every J, okay? So assume also that the limit as J goes to infinity, Fj of X exists for almost every X. Okay. All right. So under those assumptions, I get the same conclusion as I did for the monotone convergence theorem. Okay, so the integral over I, limit j goes to infinity, j d lambda is equal to the integral over I f. Sorry, I haven't defined f, so let's just limit j d lambda. And again, this is pointwise convergence. Okay, and included in my hypotheses is that that pointwise limit exists for almost every x. Okay, all right, and so this is exactly the property that the Riemann integral did not have. Okay, because we had a sequence of functions fj, which had this property, and it had a property like this for every g. We could have, in that example, chosen g to be just the function 1 on the interval 0, 1. Okay, but for the Riemann integral, this did not exist. But for the Lebesgue integral, it exists under in a general situation under these kinds of hypotheses. Okay, and the dominated convergence theorem is, in some sense, what makes the Lebesgue integral tick. Behind most important applications of the Lebesgue integral, and one of which we're going to look at in a second, lies the dominated convergence theorem. Okay, so this is a very, very powerful theorem, and there are people who make their living basically from applications of the dominated convergence theorem. Okay, so those are two convergence theorems. Okay. All right, so the Lebesgue integral has lots of other properties, and there's probably some that I should have stated here, but have forgotten to, but I'm going to sort of not do that, not give any more of this. Instead, what I'm going to do is I'm just going to sort of jump to the point of the Lebesgue integral for us. Okay. Because remember where this conversation started. So we began by asking, what is the completion of the space of continuous signals with compact support in the P norm for finite P's. Okay, and I told you at that time that it would take some work to describe what that completion is, and that work would involve a new kind of integral, which we now have. Okay, so let's exactly see how the Lebesgue integral helps us to answer that question. All right, so define L, and I'm going to put L superscript parentheses P, because we'll get rid of the parentheses here in a second. Okay. Okay, and so this is going to be, basically this is going to be the same thing as our guess. Our original guess we called, remember, R superscript parentheses P. And the definition in that case was exactly this. But for the Riemann integral. Okay. And so the difference is going to be in this case, this works. Okay, but this makes perfect sense. Okay, so so these are functions whose modulus or absolute value to the power of p is integrable. Okay, and for f in one of these spaces, LP, sorry, jumped ahead of myself for a second. We defined the norm, except we're going to see that it's not a norm, but in an uninteresting way. Okay. All right. Okay, so there's now when we talked about the Riemann integral in this setup, so this was the Riemann integral and this was the Riemann integral, there were two problems with this class of functions, which we called RP. And one was that this wasn't a norm. And the other was that there were Cauchy sequences in here which didn't converge. Okay, so the second one is a crippling defect, but the first one also exists here for the Lebesgue integral, but it's easy to get over that. Okay, so just as for the Riemann integral, this is not a norm. Okay, and it fails to be a norm because there are non-zero f's with zero norm. Okay, and the example we gave for the Riemann integral is just as valid here, and that is just take a function which is zero everywhere except at a single point. Okay, so that's not zero, but it has zero norm. Okay, so to get over this, we define an equivalence relation on L super parentheses P. We'll say that these are equivalent. If f of t is equal to g of t for almost every t. Okay. All right. And so it's easy to see that this is in fact an equivalence relation. So f is equivalent to itself. If f is equivalent to g, then g is equivalent to f. And if f is equivalent to g and g is equivalent to h, then f is equivalent to h. Okay, so the second one uses the fact that the union of two sets of measure zero is a set of measure zero. Okay. All right, so then denote by LP without the parentheses the set of equivalence classes. Okay. And we're going to denote. Okay, so if you take an F and you take its equivalence class, so with parentheses, square brackets around it to denote equivalence class, I'm going to define this by this exact same formula. Okay, and this definition will be independent of the representative of this equivalence class, because if F and G agree almost everywhere, and you choose another representative G, then you're going to use the triangle inequality. Like so, kind of to show that the norm will be the same for I put plus G, I should have put minus G, that the norm is going to be the same here for if you choose a different representative G. Okay, right, so that's you can define a norm. Okay, so there's some work you need to do here. So you need to show that this set of equivalence classes is a normed vector space. And of course, the norm is this thing that I just defined. Okay, so you even need to show that this is a vector space. You need to show that the operations of addition and scalar multiplication are valid. Okay, so you need to show that things like this. Okay. And you need to verify that the triangle inequality and all the norm properties are satisfied. All right, so all of these things are more or less routine to prove. Okay. All right, so a key part of this is the following fact, that if F, we're working with T here, is non-negative, so then F of T equals 0 for almost every T, if and only if the integral F is equal to 0. Okay. All right, so that's a fact that shows up when you try to verify all of the things that you need to verify. Okay, so so F of T being 0 for almost every T simply means that F, according to our equivalence relation that we defined up here, it means that F is equivalent to the 0 function. Okay, so F being equivalent to the 0 function is the same thing as F having a 0 integral. All right. Okay, and that's for non-negative Fs, and then for not necessarily non-negative f's. You can replace that with absolute value. Okay, good. All right, so then, so now we have this normed vector space, LP with this norm, okay, and then the fact of the matter is that LP is a completion of CPT 0 Okay, so completions are not uniquely defined. Okay, so it's a completion, but every two completions are norm isomorphic. Okay, so let's make sure that we understand what this thing is saying. Okay, so first of all, in order to be a completion, okay, there has to be an injective mapping from here into here. Okay, and that injective mapping, okay, so the injective mapping of C0 CPT F into LP. Okay, and the completion requires that you have such a thing, right? So if this is going to be a completion, part of the definition of completion is there has to be such an injective mapping. Okay, and it's obvious. You just take a continuous function signal f with compact support, and you map it to its equivalence class. Okay, now this mapping is injective, I claim. Okay, and that is because of the continuity of f. Okay, so you have an f, and so you want to show that if the equivalence class of f is equal to 0, then f must be equal to 0. But if the equivalence class of f is equal to 0, then that must mean that the integral of the norm of f is equal to 0. Okay, and then continuity of f allows you to conclude that f must be equal to 0 by arguments that we've seen before, right? So we've done this a couple of times where we've had a continuous function, and if the integral of the continuous function is 0, then the function must be 0. And so remember what the argument was. If it's not 0, then it's not 0 at some point. Say it's positive, then it's going to be positive around some interval, and that will then prohibit the integral from being 0. Okay, so continuous functions for whose norm has a 0 integral must be 0. Okay, so it gives the injectivity of that mapping. All right. Okay, good. So that finishes where we started. And so we've come full circle to giving an answer to an important question that we had, building the completion of this thing. And one of the complicated things here, which isn't that complicated to deal with in practice, but it's something worth pointing out, is that this is not a space of functions, right? This is close. It's a space of equivalence classes of functions where two functions are equivalent if they agree almost everywhere. Okay, and so we have this curious situation where we start with some collection of signals. All right, and then the completion is not actually a collection of signals; it's a collection of equivalence classes of signals. And this points out one of the difficulties of completion as a general concept, and that is that a completion may not be comprised of the same kinds of things that you started with. Okay, a completion can be sometimes difficult to understand what it is, and this is a perfect illustration of that. So we had this relatively simple incomplete normed vector vector space, whose completion, first of all, takes a lot of work to describe. Okay, a new theory of integration had to be developed to describe that, and even after you develop that new theory of integration, you need to not work with integrable functions, but equivalence classes of integrable functions. Okay, so that finishes part of our story. So what I will do next time is kind of summarize where we're at right now, and then we'll go from there. Okay.